A coronal mass ejection fired from the Sun on June 9 and again on June 11, 2026, is delivering glancing blows to Earth's magnetic field at this precise moment, June 13, 2026, and what makes this event scientifically alarming is not merely that the storm is here, but that the CME which preceded it in early June accelerated between two spacecraft positions 0.13 astronomical units apart, gaining speed across the interplanetary void when every model predicted it should have been slowing down, and no one in the global space weather monitoring community has yet produced a complete explanation for why that happened. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: NOAA's Space Weather Prediction Center, the European Space Agency, NASA's Solar Dynamics Observatory, NOAA's Space Weather Scales documentation, spaceweather, and peer-reviewed research published in the astrophysical journal Letters in Space Weather, but official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed, the data is public. The responsibility to check belongs to all of us, but that is not even the complete picture. The geomagnetic disturbance pressing against Earth's magnetosphere right now on this morning of June 13, 2026 is the visible surface of something older, something more connected, and something that our most sophisticated planetary protection infrastructure was never fully designed to survive at scale: the G2 conditions. Confirmed for today, and the residual G1 activity forecast for June 14th are not the headline. The headline is what science discovered this week about why a previous CME in this same season of solar activity broke one of the most fundamental rules of space weather physics, and what that discovery means for every power grid, every communications satellite, and every transformer-dependent hospital, water treatment facility, and financial exchange on the planet right now. The Sun is in a period of elevated volatility. Solar Cycle 25 reached its official maximum in October 2024, when NASA and NOAA jointly confirmed the peak had arrived earlier and stronger than the International Prediction Panel had forecast back in 2019. June 2026 sits on the declining slope of that maximum, but the descent is not smooth, and it is not fast. Sunspot numbers remain significantly elevated compared to the quiet years of 2019 and 2020. What this means in practical terms is that the Sun is still capable of producing events that were expected to belong to the peak months, and NOAA's Space Weather Prediction Center and space weather researchers have formally characterized the window from early 2026 through mid-2027 as a period of sustained elevated risk for satellite infrastructure and high-latitude power grids. We are inside that window right now. We are not approaching it. Understand what a coronal mass ejection actually is before you accept the numbers it carries. A CME is not a beam of light. It is not radiation in the classical electromagnetic sense. It is a physical object, a bubble of magnetized plasma, a cloud containing billions of tons of solar material torn from the Sun's outer atmosphere and launched into space. According to NOAA's Space Weather Prediction Center, CMEs travel at speeds ranging from slower than 250 km per second to as fast as 3,000 km per second. The fastest Earth-directed CMEs can reach our planet in as little as 15 to 18 hours. The slowest take several days, but what determines the damage a CME can do when it arrives is not just its speed, it is the orientation of the magnetic field it carries. When that embedded field points southward antiparallel to Earth's own magnetic field, the two fields couple. They merge at the boundary called the magnetopause. The Sun's plasma crosses into Earth's domain, flows down magnetic field lines toward the poles, and dumps energy into the ionosphere and the upper atmosphere. That energy then induces electrical currents in everything long and conducting at the surface: power lines, pipelines, submarine cables, and the iron cores of high-voltage transformers. Now consider what was published this week in research retrieved from peer-reviewed sources, the study that dropped on June 13, 2026 itself today, and that has already begun circulating through the space weather monitoring community. A November 2021 CME was tracked by two spacecraft, the ESA and NASA Solar Orbiter, positioned at 0.85 astronomical units from the Sun, and the NASA WIND spacecraft positioned at 0.98 astronomical units, essentially at Earth's doorstep. The same CME passed both instruments in sequence, and between those two measurement points, separated by just 0.13 astronomical units, that CME did not slow down. It accelerated in every standard model of CME propagation. A fast CME plowing into slower ambient solar wind should decelerate, the way any fast-moving object decelerates when it meets resistance. This one did not. According to researchers publishing in the astrophysical journal Letters, the only explanation that fits the data is that the CME was carrying an internal energy source, an unseen engine that was actively driving it faster, even as drag physics should have been working in the opposite direction. They call it an internal magnetic reconnection process within the CME's own structure, a process that was invisible to our instruments as the event was occurring and only reconstructible after the fact from spacecraft data. And here is where this account becomes genuinely significant. If a CME can accelerate unexpectedly between its launch point and Earth, then the arrival time forecasts that grid operators and satellite managers rely on to prepare their systems carry an error margin that current modeling cannot fully quantify. The question is not whether another CME will accelerate without warning. The question is when. The CMEs arriving at Earth this weekend, the ones confirmed by NOAA and spaceweather, live as delivering glancing blows to the magnetosphere on June 13th and June 14th, 2026, were launched from the Sun on June 9th and June 11th. They were tracked, they were modeled, their arrival was forecast, and that forecast has been largely accurate. This is the good news in the data. But the June 2026 solar season has already demonstrated, in the first week of this month alone, what the Sun is capable of producing without significant warning intervals. On June 3, 2026, active sunspot region R4455, a region described by space weather analysts as magnetically complex, with an anti-hail configuration, continuous magnetic flux emergence, mixed polarities, and substantial magnetic shear, produced 3 significant eruptions in a single day: an M9, 3 flare at 1:36 UTC, an M7, 7 flare at 7 o'clock UTC, an X1, 0 flare at 11:28 UTC, 3 separate coronal mass ejections launched toward Earth in a window of less than 10 hours. NOAA's Space Weather Prediction Center issued a G3 strong geomagnetic storm watch for June 4th and June 5th. That storm arrived and was confirmed auroras reached latitudes as far south as France and New Zealand. And then, before that storm had fully dissipated, new eruptions on June 6th triggered a second G3 watch for June 8th and June 9th. The June 8th CME arrived on schedule, delivering another round of G3 conditions. Researchers note that the forecast accuracy for the June 8th storm was exceptional, correct to within hours. But exceptional forecast accuracy for one event does not guarantee it for the next, particularly when the physical mechanism that drove a different CME to accelerate mid-transit remains incompletely understood. Think about what this means for the people whose lives hang on the reliability of electrical infrastructure that was not designed with this moment in mind. Think about the city of Canada, with a metropolitan population of approximately 3 million people, a city whose relationship with solar storms is not theoretical. On March 13, 1989, a powerful coronal mass ejection struck Earth's magnetic field at approximately 1:27 UTC. What followed was documented with extraordinary precision in research published by Dr. David Bottler of Natural Resources Canada's Space Weather Group. 90 seconds. In 90 seconds, the entire hydro power grid, a system generating 21,000 megawatts and serving a province twice the geographic size of the state of Texas, went dark. 6 million people lost power. The metro closed during the morning rush. Dorval Airport shut down. Schools and businesses did not open. The blackout lasted 9 hours. The storm that caused it was rated at the highest level of the KP index, reaching what would today be classified as a G5 event, with a minimum DST value of negative 589 nanoteslas, meaning Earth's own magnetic field was compressed and distorted by that magnitude. The March 1989 storm was caused by 2 successive CMEs, the first from an X4-5 flare on March 10th, the second from an M7-3 flare on March 12th, and it was the interaction of those 2 events, arriving in sequence, that drove the system beyond what any single CME could have achieved alone. That pattern, multiple CMEs in rapid succession, each one potentially energizing the conditions for the next, is precisely the pattern the Sun has been producing. In June 2026, this is not a hypothesis. This is documented in the geological and instrumental record, and the record is entirely clear on this point. It has already happened before, it has happened more than once, and the systems now at risk are exponentially more complex than the systems that failed in 1989. The National Academy of Sciences has estimated that a rare but powerful magnetic superstorm, the kind that space weather researchers formally classify as a plausible low probability, high consequence event, could cause continent-wide loss of electricity with infrastructure damage that could persist for months and cost the United States in excess of $1 trillion, and then consider what the United States Geological Survey notes in its own published assessment. It is not the transmission lines themselves that are most vulnerable. It is the high-voltage transformers, the specialized custom-built, extremely expensive, multi-month lead time transformers that step voltage up and down across the grid. Each one can weigh hundreds of tons. The United States does not stockpile them in significant numbers. Their replacement, if damaged by geomagnetically induced currents, is measured in months to years, not days. The mechanism of that damage operates as follows. When a CME arrives and the interplanetary magnetic field it carries turns southward, it couples with Earth's field at the magnetopause. Magnetic reconnection accelerates charged particles, protons, and electrons down toward the polar regions. As they dump into the ionosphere, they create currents in the upper atmosphere. Those currents create electromagnetic fields. Those electromagnetic fields induce electrical currents in the ground itself, and those ground-level induced currents, what scientists call geomagnetically induced currents, or GICS, flow into any long conducting structure that touches the Earth's surface: power lines, oil pipelines, fiber optic cable sheathing. The longer the conductor, the greater the current it accumulates. A high-voltage transmission line stretching 1,000 kilometers in a north-to-south orientation during a strong geomagnetic storm is not simply a wire. It becomes an antenna, collecting solar energy and delivering it to a transformer that was designed to handle alternating current at its rated frequency. GICS are quasi-direct current. They saturate transformer iron cores, generating heat, distorting the waveform, tripping relays, and in extreme cases, permanently damaging the transformer itself. Now consider the connected systems. Geomagnetic storms do not affect power grids in isolation. They press simultaneously against every satellite in low Earth orbit. When the sun heats the upper atmosphere during a geomagnetic storm, the atmosphere expands, satellites in low Earth orbit encounter increased atmospheric drag. Their orbits decay faster than expected. Operators must fire thrusters to compensate, consuming fuel and shortening mission life. In a G3 event, the expansion of the upper atmosphere is measurable and significant. Starlink and other mega-constellations of low Earth orbit satellites have publicly acknowledged storm-related drag events when solar conditions intensify. During the May 2024 G5 event, the most powerful geomagnetic storm in 20 years, driven by active region R13664, which produced an X87 flare and a minimum DST index of -412 nanotesla, satellite operators worldwide reported temporary communications disruptions and elevated radiation levels. The GPS timing signals that underpin not just navigation but financial transaction time-stomping, air traffic control separation, and emergency services dispatch were affected across wide geographic areas, and the solar tectonic connection, the second global system this event reaches into, carries its own body of evidence worth examining carefully. Researchers studying the relationship between solar wind pressure variations and seismic activity have documented correlations between periods of elevated geomagnetic activity and increased seismicity in regions already under tectonic stress. This is not settled science in the way that CME propagation physics is settled science. It is a subject of active investigation, with research appearing in peer-reviewed journals over multiple decades. What is established is this: the Earth is not a passive recipient of solar energy. The upper atmosphere, the ionosphere, the magnetosphere, and the planet's crust are coupled systems. Energy deposited in one propagates into others. The precise mechanisms are still being mapped. The correlations have been observed. And here, as in so many places in the data surrounding this event, scientists choose their language carefully, and that careful language is itself the warning. The people of Troms, Norway, population approximately 77,000, live at 69 degrees north latitude, well inside the auroral zone. They understand at an intuitive and daily level what it means to live beneath the electromagnetic connection between the sun and the Earth. The northern lights are not decoration there, they are a reminder. During strong geomagnetic storms, the power systems serving Troms and the surrounding Troms-og-Finnmark County face some of the most significant GIC exposure in Europe, precisely because of the region's high magnetic latitude and the long transmission lines running across the electrically resistive bedrock of Scandinavia. What would those 77,000 people want to know if they had access to the data in front of us right now? They would want to know whether the coronal mass ejections arriving this weekend carry a southward magnetic field component. They would want to know whether the B's value, the north-south component of the interplanetary magnetic field measured at the L1 point, the gravitational balance point between Sun and Earth approximately 1.5 million kilometers upstream, has turned negative, because it is B's, more than any other single measurement, that determines whether a CME will couple with Earth's field or pass largely without consequence. B's cannot be predicted from solar observations alone. It is only measured when the CME reaches the L1 monitoring point, and by then, the CME is between 15 and 60 minutes from Earth, depending on its speed. 15 to 60 minutes, that is the entire warning window available to every power grid operator on the planet for what comes next. Not hours, not days, minutes are not hours, and in this context, that difference is everything. Think also of the approximately 29 million people living in Texas, a state whose power grid, the Electric Reliability Council of Texas, or ERCOT, operates largely in isolation from the rest of the North American grid, connected to neighboring systems through only limited direct current ties. In February 2021, a winter storm brought ERCOT to the edge of total uncontrolled collapse over a period of days. Grid operators later revealed that the system came within minutes of a complete blackout that could have lasted weeks. A geomagnetic storm severe enough to simultaneously damage multiple high-voltage transformers across the Texas grid would present a logistical challenge of a different order, precisely because ERCOT's electrical isolation means it cannot draw significant replacement power from neighboring systems the way most of the continental United States can. The vulnerability is documented. The awareness is increasing. The transformation of awareness into hardened infrastructure is incomplete. The system is not inactive. It is accumulating. Solar Cycle 25 has, as of mid-2026, already exceeded the activity levels that some of the international prediction panels projected for the entire cycle. The January 2026 event, a long-duration X195 flare from active region, are for 3-for-1 on January 18th, producing a CME that ESA models initially estimated at 1,400 kilometers per second, but which arrived at Earth approximately 25 hours later, implying a transit speed closer to 1,700 kilometers per second, generated a geomagnetic storm that reached severe G for conditions for approximately 15 hours and remained at G3 for more than 18 hours. That storm, according to ESA's own monitoring documentation, ranked among the largest space weather disturbances of solar cycles 23, 24, and 25 combined. Widespread auroras appeared across most of Europe and across the United States. The radiation storm reached S4 levels, among the most intense in GOES satellite records, and it happened in January, at the beginning of this same year. The year that contains the weekend of June 13th and June 14th. What is happening now is not happening in isolation. The June 9th and June 11th CMEs arriving at Earth today and tomorrow, producing G2 and then G1 conditions as their effects gradually wane, are the trailing members of a sequence that has not fully concluded. Active region are for 465 and other sunspot groups on the Sun's visible disk remain capable of further eruptions. NOAA's 3-day forecast, current as of the morning of June 13, 2026, indicates the greatest expected 3-hour KP index for the June 12 through June 14 window reaches 567 G2 level during the 6 o'clock to 9 o'clock UTC window on June 13. That is this morning. G2 conditions produce voltage alarms on power transmission systems, require transformer heating correction, cause HF radio communication degradation across wide areas, and driver or a visible to latitudes below 55 degrees under clear dark skies. They are not G5, they are not March 1989. But they are not background noise either. And the question the data is quietly asking, the question that researchers publishing in the Astrophysical Journal letters were also asking when they described that November 2021 acceleration anomaly, is whether our models are capturing everything that is actually happening between the Sun and the Earth in real time. Here is what the official data actually shows. We can observe a CME's launch. We can measure its speed near the Sun using coronagraph instruments aboard spacecraft like the ESA or NASA SOHO satellite. We can model its propagation through the interplanetary medium using software that has improved dramatically over the past decade. We can detect its arrival at the L1 point approximately 1.5 million kilometers upstream from Earth, giving us that 15 to 60 minute final warning. We cannot, from solar observations alone, determine the B's orientation of the field it carries until it reaches L1. We cannot reliably predict whether it will interact with a preceding CME and form what space weather researchers call a cannibal CME, a combined structure where a faster ejection overtakes a slower one and the two merge into a single more powerful entity with altered magnetic properties. And as of this week's research publication, we now have documented evidence that a CME can carry an internal magnetic energy source that drives its own acceleration in ways our current operational models do not fully capture. The forecast that said today's CME glancing blows would produce G2 conditions has so far been accurate. The forecast for the next event has not yet been issued because the next event has not yet occurred, but the Sun is still active. The region that produced June's earlier eruptions still exists on the solar disk, and the geometry of Earth's position relative to the solar wind continues to evolve. The Carrington event of September 1859 is the name scientists give to the largest geomagnetic storm in recorded history. It was produced by a CME that struck Earth's magnetic field approximately 6 hours after its solar origin, one of the shortest transit times on record. The storm's intensity, as reconstructed from historical records and geomagnetic data, surpassed even the March 1989 event by a factor of roughly 2 in 1859. The most sophisticated electrical infrastructure on Earth was the telegraph network. The currents induced by the storm set telegraph offices on fire. Operators reported receiving and transmitting messages with their equipment disconnected from power supplies, using only the current the storm itself was driving through the lines. When the same physics is applied to a 2026 grid, to a network of hundreds of millions of high-voltage transformers, billions of connected devices, and an internet infrastructure whose physical layer runs through undersea cables and satellites and data centers that cannot simply be shut down and restarted without consequence, the scale of that 1859 event becomes something the mind must work to fully receive. This has already happened once. The record of it is still preserved in the magnetometer data, in the charred telegraph poles, and in the scientific literature. The question is not whether a storm of that magnitude is possible. The evidence establishes that it is. The question is not whether our infrastructure would survive it unmodified. The evidence suggests it would not. The only remaining question, the one the data holds open without resolution, is when no instrument in the global space weather monitoring network can answer that question today. NOAA's Space Weather Prediction Center operates continuous monitoring. NASA's fleet of heliospheric observation spacecraft maintains real-time watch. The European Space Agency's network tracks solar activity around the clock, and what all of those systems share is the same fundamental limitation. They can tell you what has launched. They can estimate when it will arrive. They cannot tell you with certainty what orientation the field it carries will have when it reaches Earth. They cannot tell you whether the CME you are tracking is carrying the internal engine that caused one event in November 2021 to defy all predictions. The monitoring is in place and detection is possible, but prediction is not, and that sentence, spoken in the measured language of senior space weather scientists who choose every word with care, is the most precise warning the data offers. The sun rose over the Atlantic coast of North America on the morning of June 13, 2026, as it always does, with no visible indication of what is moving through the 150 million kilometers between it and us. The space between is not empty. It is filled with a solar wind that averages 400 kilometers per second, and occasionally surges past 800. It is threaded with magnetic field lines that tangle and reconnect and release energy in structures that take days to traverse and seconds to cause cascading failure at the other end. The CMEs from June 9th and June 11th are in that space right now, moving toward us and already arriving, pressing against the magnetosphere that has protected biological life on this planet for billions of years. The magnetosphere will hold. It has always held. But the transformers attached to the grid that sits beneath it are a different matter entirely, because they were built by human beings in the 20th century, and the 20th century, for all its engineering achievement, had no G5 storm against which to test them at full planetary scale. The planet beneath our feet has been cycling through solar maximums for as long as the sun has burned. 11-year cycles of activity and quiet, peaks and troughs of sunspot production, each one bringing its CMEs and its geomagnetic storms and its brief ionospheric disturbances that our ancestors could not measure and did not understand. What has changed is not the sun. What has changed is what we have built in the path of what the sun does naturally, reliably, and without awareness of us. Somewhere in the archive of the hydro power system, there is a record of the moment on March 13, 1989, when 21,000 megawatts vanished from the grid in 90 seconds. That record has been studied by engineers and space weather researchers for 37 years, and the grid in those 37 years has grown larger, more complex, more interconnected, and more critical to human survival than anything that existed in 1989. The storm that is arriving today is G2. It will likely fade to G1 by tomorrow. The one after it, whenever it comes, may be different, and the internal engine that drove one CME to accelerate between two spacecraft this season, the engine that no model captured in real time and no forecast predicted, is still there, inside every ejection the sun produces, waiting to be measured after the fact if the instruments survive long enough to record what happened. The geological record does not lie. The sun has done this before. The sun is doing a version of it right now. And the largest transformer in your city, the one stepping 500,000 volts down to something a home can use, has never experienced a Carrington scale field compression and has never needed to. That is the question the data leaves open. That is the silence the instruments cannot fill. That is what the sky above you is carrying right now in the solar wind you cannot see and cannot stop moving at several hundred kilometers per second toward the magnetic field that, for all of human history, has been the one thing standing between the surface of this planet and the full force of what the sun continuously sends our way.